Greetings, Calc students. In this video, we will be exploring the concept of volume from a two-dimensional area that we are all familiar with now, I hope, to a three-dimensional volume. Units squared becoming units cubed. How does that come about? Well, if we want to transfer from here to here, in this particular example, we would need to duplicate that heart several times, creating a tunnel of hearts or a loaf of bread made of slices of hearts. These cross sections are all the same size, they're all the same shape, but basically we've duplicated them over this depth. So that will be our third dimension. So the cubic units come from the area multiplied by the depth. This is one way to determine volume, and it's actually going to be the last way that we look at in this section, but it's probably the most intuitive way to start. Another way we could create a volume from this area is by putting this heart on a stick, call it an axis, and spinning it. If I turn that heart round and round and round and round and round and round, not so easy to draw. Imagine it might look like an apple. An apple with a point at the bottom, maybe a pumpkin, whatever you want to picture here. But that would also be a volume. And that's the type that we're going to work on in this video through two examples. It is called a rotational volume, or a volume of a revolved solid, where we revolve it about an axis. So there you have it. Now this first type that we're going to do is probably the most basic, and then we will build, of course, to things that are more complex. The first example I like to do for creating volume is to work with a sphere. Now, young people kind of have a misconception that a sphere is a circle. And if we're calc students now and we want to pretend that a sphere is a circle with some thickness to it, you can't really do a depth because then you create a cylinder. However, we could take that circle and spin it either on an axis like this or on an axis like that. And actually we don't need the full circle. So what I've provided here in this example is the equation of a semicircle, radius 4. And this will turn into a sphere if we rotate it on the x-axis. So let's see how that's going to work. It's quite the jump to 4, but work with it. So we're going to take this area, this region, everything in here, and we're going to rotate it. So picture the semicircle being rotated around, rotated around, rotated around, rotated around, the entire thing. Now as I rotate, I'm creating these discs. Actually, I'll try to do a better job and it'll look like a ball of yarn. And every disc that goes around and around here has a different radius. Now that's going to be an important part to this process, finding the radius, expressing the radius I should say, because every radius is different. Like here's a section, and it's got a different radius and a different thickness perhaps than this one out here. Check out that radius. It's a lot smaller, but it still creates a disc. And each of these discs will have a thickness. That thickness extending here to here. Arbitrarily we will call that delta x. And just like with area, we could have a thickness of delta y, but in this particular example we're going to work with the delta x. Notice that the radius keeps changing, but it is that vertical measure that we call y. And what that is for each one of these discs very much depends, here's the biggest one, depends on the value of x. And so we will use this expression for the radius. Now remember we said we were going to accumulate area over a third dimension. In this case we're going to accumulate circular areas. Each disk has an area. Radius squared is a part of it, times pi of course. Pi times radius squared will give us the area of each one of these disks. And then, to go from area to volume, we need to give it a thickness. And remember we said that thickness was, for each disk, was that delta x, or in the Latin, dx. Now if we accumulate all of these disks from -4 to 4, we should find that we get a volume. So if we use the particular expression here, square root of 16 minus x squared, square that, because that's the radius, and evaluate from -4 to 4. The last thing I would do is multiply by pi, whether I'm doing this by hand or with the calculator. You should get a nice answer of 33.510 units cubed. And let's remember to label cubic units, because this is not an area anymore, it is a volume. 33.51 cubic units. Now of course you might want to do a quick check if you know it's an exact sphere. 4/3 pi r cubed. If the radius is 4, that is way off actually, so I'm going to pause and correct my answer. How about this for a second try? 268.083 cubic units. Yeah, I kind of faked it and tried to do it in my head and quickly with my calculator, and it didn't work. But just a quick note here, this problem would be pretty nice actually to do by hand if you had to. Let's say it's on the non-calculator part of the test, because a square cancels a square root. This will basically be the antiderivative you need to find for 16 minus x squared. If you wanted to work this out, don't forget to lastly multiply by pi, and then you'd have probably the nice exact form of the answer, like this. So 268.083 would be that volume of that sphere found by revolving the semicircle about the x-axis. For our last example, I've already created the region. We have created a volume by bounding the region. These are the bounds. Usually those will be given to you. Those are like the outline, I guess, of the region. And then it becomes three-dimensional when we revolve about the x-axis. So again, we're revolving about the x-axis. We'll do a quick hypothetical at the end here about what it would look like if we had revolved about the y-axis. But if I just take a few points at a time here and revolve, 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 round and round, and all the spaces in between getting smaller and smaller, we seem to be creating a three-dimensional triangle, also known as a cone. It's a cone. Not every region you find a volume for will be a known geometric figure, but in this case we're working from kind of basic ideas, so they are. Now here we're just going to focus on the setup. So again, we're going to look at disks, because each small section, as we kind of maybe pull one out at a time and call it a thickness of delta x. If we can find the area of that circular disk, which will base it on its radius, multiply by that thickness, area times thickness will give us volume. And again, that thickness is as thin as we could possibly get it. That is the delta x part. So once more, the radius here will depend on y, and y depends on x. So this expression will actually be our radius, right? Because each of these vertical measures are those points on that line, the biggest one being here at the base. So the radius, if we square it, headed towards the area of a circle, multiply by pi, .566 cubic units. That number actually is very nice if you work it out by hand. It is 4 pi. but we can give the approximate value. AP likes us to go to 3 decimal places. And so there we have it. The volume would be cubic units revolving about the x-axis. Now, last thing I promised was a hypothetical. What if we had revolved on the y-axis instead? Then we would kind of see these values duplicate in this direction. And in that case, then we'd still have disks. That circular motion of revolving creates circles. And each one of those disks, though, would have a thickness. The thickness in that case would be delta y. And the radius, this is fun to talk about, the radius would have been, I don't know if you're going to be able to see this, the radius would have been this value here, which is horizontal, and the radius in that case would be x. So you'd have to rearrange your equation so it would solve for x. In summary, in this video, you can read, we calculated some volume. Just like with area, it can be done in more than one way. And that will depend, in this case, on which axis you're revolving on. Stay tuned, more to come. There will be 2 other techniques for finding volume. The volume of revolution can be done not just with disks, but there's also a way to calculate volume for cross sections of desired shapes and on a certain base. So that will be coming as a continuation of this section 7.3. But I encourage you to get some practice, and we will finish this up in the coming days. Mrs. D, signing out.